Today we're going to look at saturation and solubility. Now we've already talked about solubility a little bit, so hopefully some things will come back to you during this lesson. So the goal for today is to interpret solubility curves, right, which is a graph depicting solubility as a function of temperature. We'll get into that in a little bit. And to distinguish among, or kind of define, saturated, supersaturated, unsaturated solutions. What do those three words mean? Okay, so before we begin here, right, I'm going to have you pause pretty quick into this video because I want you to do a little do now before we get started, just so you get your head in the right place. Ask yourself, right, does sugar dissolve better in iced tea or hot tea? You probably already know the answer to that, but why do you think that is? Right? Why do you think sugar dissolves in one of those better? And you probably know which one it does dissolve better. And then I want you to define, and this might take you a minute, right, a little longer, solute, solvent, and solution. Now, we looked at those terms in lesson 6 of this unit, which was not online, so you can still go back in Google Classroom and find the handout. Also, the reading I attached to this lesson, I believe, defines those terms. So if you're struggling, you can always look back there. Okay, so go ahead and pause the video. Okay, so sugar dissolves better in hot tea, right? The hotter that water is, up to 100 degrees, because you can't get water hotter than that at sea level, the better sugar dissolves. The better almost all substances will dissolve. But why? Well, if you think about what temperature is, it's it's a measurement of average kinetic energy. So we're talking about the movements of those liquid particles. We're probably talking about water. In terms of tea, we're definitely talking about water as the solvent, right? Solvent is the thing that does the dissolving. So for our purposes, it's almost always water, right? It doesn't have to be. For example, you could mix, some butter into oil. Those would dissolve, and in that case, right, the oil would dissolve the butter. The oil would be the solvent. But in this course and in most of life, right, the solvent is water. It's kind of the universal solvent, right? It's everywhere. So, right, it's about the motion of those particles in a hot liquid, right? They're moving faster. They're able to break apart more of the sugar. In this case, right, dissolve more of those particles simply because of the speed at which they're moving. So let's define these terms before we go into the lesson. I just defined solvent, right? Solvent is the thing that does the dissolving, whereas the solute is what gets dissolved, right? So think about salt water, okay? In salt water, like the ocean, the solvent is water, the solute is the salt. Okay, and that forms when you have a solute dissolved in a solvent. That's a solution. And remember, a solution is a homogeneous mixture, meaning it's made of different compounds. There's different substances in there, but it looks like one thing. Other examples of solutions, right? Kool-Aid, right? Looks like one thing, but we know there's food coloring, there's sugar in there, there's water. There's plenty of other examples. Pretty much any beverage besides, well, even water from your tap is a solution because it has dissolved minerals in it, and you can't tell. It looks like one thing. So pretty much everything you drink is a solution, with some exceptions, obviously. Like milk is not technically a solution. I believe that's a colloid, but don't worry about that. Okay, so good. Hopefully we got those terms defined. So we're going to talk about saturation first, and we're going to look at these three terms here. Saturated, supersaturated, and unsaturated. Okay? So first of all, supersaturated, right? We're talking above this line. So let's slow down a little bit here. Let's look at this graph. Right? Always look at the axes, right, when you're looking at a graph to know what's going on. Now, there's no numbers here, so it's just a very general graph, right? But we have temperature on the x-axis, and we have, this is a little more confusing, we have solute, so dissolved particles, or in this case it's measured in grams, so the mass of the dissolved substance per 100 grams of water. It's kind of a weird way to measure water, but that's how we do measure solubility, okay? So it's the amount of grams of, let's pretend it's salt water, right? So it's the amount of grams of salt per 100 grams of water, all right? But this could be anything, right? The solute could be anything dissolved in water. So in a supersaturated solution, okay, the solute is actually holding more solute than it should, right? It's unstable, right? This won't last. A little vibration, or if you knock it, you'll probably see some of that solute fall out of solution, perhaps. Not always, right? You can make supersaturated solutions that kind of stay supersaturated. We'll talk about that in a minute. So yeah, if above the line, right, is supersaturated, then below the line is unsaturated, and it can hold more solute. Right? Supersaturated has more than it should. Unsaturated means it can hold more if it wanted to. So if we think about, right, let's keep it with salt water, I guess, right? You put a little bit of salt in water, right? You could probably still put more in. That's unsaturated. Now, you could have a situation where there's more than there should be. That's supersaturated. Okay? So with those two definitions in mind, we're going to answer some questions here. According to the graph and the definitions that we just went over for supersaturated and unsaturated, what do you think saturated means, right? Also, what could you do to a saturated solution to allow more solute to be dissolved? Look at that graph. Look at the axes. Okay? And then how do you think a supersaturated solution is made? You can actually make them, right? There's a very common one, especially in the South, that's made, which I'll talk about in a moment. But first, I'd like you to pause the video and answer these three questions. What does it mean to be saturated? How could you put more solute, right? What could you change about the solution to add more solute? And then how do you think a supersaturated solution is made? So go ahead, pause the video. Okay, so, right, when a solvent will accept absolutely no more solute, it's said to be saturated. So it's kind of like full, right? So I have a cup of water, I'm adding salt or sugar, whatever. So I'm adding salt to it, and when I get to the maximum amount of salt that can be dissolved, that's saturated, right? It's full in a way, okay? Now we're going to see this term saturated in a later unit. It's going to mean something different, but also you'll see a similarity. So look out for that in the very last unit we do on organic chemistry, okay? But for right now, we're talking about solutions, and it means the solvent has the maximum amount of solute. Now, you can always heat up a saturated solution to allow more solute to dissolve. Look at the graph, right? The higher the temperature, the more solute it will take to be saturated, meaning the more solute that you can dissolve in that solvent, the higher the temperature. Now, this is true for most substances, most solid things, but we'll look at more specifics in a bit. So you can make a saturated solution by heating up the solution, saturating it, and then cooling it back down, right? So say we're here, it's saturated, we heat up the solution, so now we're unsaturated, so we add more solvent to make it saturated, and then we cool it down, and we're supersaturated, all right? And you can actually do this. This is how you make sweet tea, right? Sweet tea has like a ridiculous amount of sugar in it, super unhealthy. Of course, it's delicious. It's got a stupid amount of sugar in it, right? But what they do is they heat it up. They make like hot tea, put as much sugar in as they can, so they saturate it. Then they cool it down, right? Throw it in the fridge, cool it down, and now there's actually more sugar dissolved in that liquid than you could get if you tried to dissolve it in that liquid at the temperature it's at, as iced tea. Right? So sweet tea actually is a supersaturated solution. It's also very unhealthy. Don't drink it. Okay. Good. So, what kind of factors affect solubility? So how can we, change the solubility of a substance? So if you remember, like dissolves like is an adage that we've mentioned before when we talked about polarity and solubility. So like dissolve like means polar substances will dissolve other polar substances, and non-polar substances will dissolve other non-polar substances. Okay, so a couple quick examples. Polar substances, right? That's salt in water. Even though salt is technically ionic, you can think of ionic as being like superpolar, right? Sugar in water. Okay, sugar is Polar. Water is polar. Non-polar, I gave this example earlier. Fats are non-polar, so you could mix butter and oil and they would dissolve. That's non-polar dissolving in non-polar. Any kind of hydrocarbon, right? But yeah, you get it, hopefully. So the stronger the attractions between the solute and solvent molecules, the greater the solubility. All right. So remember, polar molecules are like magnets. So if you have one magnet, which is like water for us, and you dissolve and you put sugar in it, which is essentially another magnet, right? That attraction is going to be very strong, and you're going to have greater solubility. Okay. Um, yeah. So similar intermolecular attractive forces tend to be soluble in one another. So that's just a fancy way of saying like dissolves like, polar dissolves polar. The more polar it is, the better it will dissolve in water, right? Nonpolar dissolves nonpolar. Now what about pressure? So if we're thinking about a gas, so this is just for gases, right? We don't really talk about pressure when we're talking about solids or liquids. You can, liquids at least, but we're talking about gases here. So the solubility of a gas in any solvent is increased as the partial pressure of the gas above the solvent increases. Okay, that sounds super confusing, but it actually is not. So this visual makes it very obvious, I think, right? So you have gas above a liquid, right? Has a certain pressure, right? We call it a partial pressure, but that doesn't matter. We have gas above a liquid, right? If we increase the pressure of that gas above the liquid, we're going to force more particles into the solution, right? So, I mean, if you look at it, right, you're basically pushing gas particles into the water. In this case, it's water. So if you increase pressure of a gas over a liquid, you're going to increase the solubility because you're literally pushing, right? You're pushing those gas particles into the water, forcing them to dissolve in a way. Um, yeah, so I think that one is pretty straightforward. It's easy to wrap our heads around. This picture does a nice job of illustrating the pressure effects of a gas in terms of solubility. Okay, temperature. This is the big one. This is the one that you'll, see most often in questions, Regents-wise, or just in this course too. So, well, before I get there, right, this table G, all right, I think this is the first time we've used this one, so introducing you to table G here. These are solubility curves. So this is, we looked at, way back here, this is a solubility curve. It's very simplified, right? It's just, there's no substances labeled. It could be anything. There's no numbers. So this is a very much more information here, and it has a whole bunch of different substances that we're looking at. So again, though, look at the axes are the same. Temperature, solute per 100 grams of water. So it's the same axes as that first graph we looked at. It just has a bunch of different substances on it. And you'll notice most substances, right, as temperature increases, solubility increases, but not all of them. NH3, SO2, right? HCl. Okay, a few of these substances actually decrease solubility as temperature increases. So solubility of most solid solutes, all right, things are dissolving, in water increases as the temperature increases. There are exceptions, NH3, HCl, SO2, whose solubility curve actually goes down with increasing temperature. Okay, so you can take a look at this, right? You're going to be using this today to answer some practice questions, so I recommend having your reference table ready to go, digital or not. So if we're talking about gases in water, right, the solubility of gases in water will decrease with increasing temperature. Okay, so, right, the greater the temperature of the water, the less dissolved gases, the less dissolved gases will be in there. So you can see this when you're boiling water, right, and you see those bubbles start to form before it's boiling, right? Those are the gases dissolved coming out because you're heating up the water, the particles are moving faster, they're kicking out the gases, basically. Don't do this, but if you tried to heat up a can of soda when it's closed, I think you know what would happen. It would explode because you have all the dissolved carbon dioxide gas in the soda, right? And it's a closed container, so it's going to the liquid, as you heat it up, is going to kick out the gas, and that gas doesn't have anywhere to go, so it's going to make the soda can explode. But it's also why if you leave soda out, it goes flat, right? Room temperature is warm enough to kick out carbon dioxide out of a liquid. So if you leave a can of soda out that's opened, or a glass of soda or whatever, eventually, right, you take a sip and it tastes weird and there's no bubbles. It's because, the weird taste has something to do with it, carboxylic acid. But there's no bubbles because all the carbon dioxide was forced out of the solution. Because as you increase temperature, the solubility of gases decreases. Okay. Cool. So we're going to do some example problems here using table G. Right. So we're looking at this table here. I'm pointing at my screen like you can see that. Okay. So let's do a couple examples. I'll throw up some check for understanding questions. You can try those, and then I'll post a homework, and that'll be it for today. Okay, so at what temperature will the solubility of KNO3, that's potassium nitrate, be 60 grams per 100 grams of water? So right when you read these questions, what am I looking for? At what temperature? I'm looking for temperature, okay? So 60 grams of KNO3 and 100 grams of water. So if I go to table G, okay, I got to find the right substance. There's KNO3. So here's the KNO3 curve, okay, and it said 60 grams. Oh, this is temperature. Got to be careful, right? Look at your axes. 60 grams, here we go. So I go and I hit the curve. That's KNO3. And it's asking me for temperature, so I'm going to drop it down. So, I'd say like 37, 38 degrees Celsius. So at like 37, 38 degrees Celsius, the solubility of KNO3 would be 60 grams per 100 grams of water. Okay, again, really quick. KNO3, 60 grams per 100 grams of water. I go to the line. What temperature is that? 38, about. Okay. All right, number 2 here. How much NaNO3, so sodium nitrate, different substance, is needed to saturate 50 grams of water at 40 degrees Celsius? Okay, this one tries to trick you because look at the grams of water we're talking about. Remember, our table is based on 100 grams of water. It's asking about 50 grams of water, but we don't have a table that shows that, so we're gonna have to double, right? Or I guess cut in half the answer that we get. Because if we look at NaNO3 and we go to 40 degrees Celsius and see how much can be saturated, let's do that. NaNO3 is, there it is, up here. 40 degrees Celsius is here, temperature's on the X. I go up, find the line, that's NaNO3. Right, we'll call that, 106 grams? But that's 106 grams in 100 grams of water. So if we're talking about 50 grams of water, we have to cut that in half, right? So it's not 106, it's 53, which is half of 106, right? Okay, so you might want to replay this part of the video, right? Because number 2 here, it's a little tricky. You got to remember, our table is based on, these are the grams that can dissolve in different temperatures in 100 grams of water. So we did our 40 degrees, went up to NaNO3. A lot of people might just stop there and say, oh, you can dissolve, 106 grams. Well, sure, in 100 grams of water, but if you only have 50, you can only dissolve half as much because you have half as much water. So instead of 106, it becomes 53 grams. Okay, so that one's a little tricky. Go ahead and rewind if that was a little too much. Slow it down, right? The beauty of this is you can listen to it as many times as you want. Okay, so once you think you understand these two, go ahead and try out these questions. So at least 1 through 3, and then why not try number 4, right? So go ahead, pause the video, do all of these questions, 4 if you're feeling bold, right? And then we will continue. Okay, So hopefully you took some time to get these questions down. So let's define these three terms. Unsaturated and we're talking about solutions here, right? An unsaturated solution, it can hold more solute. You can dissolve more stuff in it. A saturated solution is kind of like full, right? It's that you've dissolved as much as you can. And a supersaturated solution means that, somehow the solution actually is holding more than it should. And that usually happens because first you heat it up, saturate it, cool it down, and now it's holding more solute than it should. The solvent is holding more solute than it should. Okay? Number two, in an experiment, 100 grams of water, okay, that's good because we know our graph is based on 100 grams of water, right, is saturated, meaning it's full, with NH3, okay, and it's at 30 degrees. If the temperature, so you know what, I'm going to stop right there in this question because I want to know, it's telling me how much is that, right? 100 grams of water, 30 degrees, NH3. NH3 is here, 100 grams of water, that's our thing. 30 degrees, I go up to the line, it's a hard one to see. 30 degrees, NH3, so like right here. So that's 45 grams. Okay, so I'm going to write that down actually, right? So we're talking about NH3 at, was it 40 degrees Celsius? Let's make sure. 30 degrees Celsius. 30 degrees Celsius, 100 grams of water. So, So that can hold, right? We said about 45 NH3, 30 grams. Yeah, about 45 grams. So 45. Go back here. 45 grams, right? I can hold that much in 100. This is in 100 grams of water. Okay. Cool. So that's not the question asks, though, right? We have to, I just wanted to get that down. So if the temperature is then lowered to 0 degrees, okay, how much additional NH3 will be needed to resaturate the solution? Okay, so let's look at our graph here. If we decrease the temperature all the way down to 0, then I can dissolve, let's see, that looks like 90, right? I can have 90 grams. Okay, so at 0 degrees Celsius, I can have 90 grams. It takes 90 grams to saturate it. So the question was asking how much more additional, so the answer is not 90, right? That's the total amount. How much more additional NH3 will I have to add? So I have 45, I want to get to 90. Well, that's another 45. So I'd have to add 45 grams of NH3 to resaturate the solution. Okay? And if you notice, NH3 is one of those weird substances that actually increases solubility when you decrease the temperature, right? Most things, if you decrease the temperature, you decrease solubility. In this case, NH3 is one of those weird ones, right, with the downward sloping curve, whereas most things curve up. Okay? So you'd have to add 45 grams of NH3 there, to resaturate that solution. All right, you'd need a total of 90, but you need to, right, it says how much additional? You need 45 more. Okay, so that one's a little bit tricky. At what temperature, number 3, what temperature do NH4Cl, it's ammonium chloride, and HCl, that's hydrochloric acid, have the same solubility? All right, so I think I'm going to look for where those two lines cross, probably, right? So NH4Cl and oh, look at that, right there, right next to each other. Same solubility, yeah, so they have a solubility of like 56 grams in 100 grams of water at, call it 58 degrees Celsius, right? So both of these substances, HCl and H4Cl, at 58 degrees Celsius have the exact same solubility, right? It's where these lines cross, okay? So I think it asks for the temperature. Yeah, so the temperature would be 58 degrees Celsius, which is, right, where these two lines cross. They have the same solubility. Okay, for the challenge question, this one's pretty interesting. So sulfur dioxide is one of the major gases that reacts with water in the atmosphere to produce acid rain. And I was asking, where do you think we'd have SO2 would have more of an effect, and why? Well, if you think about the solubility of gases, right, the greater the temperature of the liquid, so water in this case, the less gas you can dissolve. So in places where it's colder, right? I mean, the atmosphere gets pretty cold when you get up there, so this can happen anywhere. But in colder climates, you can actually dissolve more sulfur dioxide in the clouds, which are, which is just about to be, it's basically liquid water, right? It's about to be liquid water. It can dissolve more sulfur dioxide. And when it does that, there's a reaction that takes place that turns it into, I believe, sulfuric acid, which is one of the components of acid rain. But it's about the temperature, right? Colder clouds, basically, can dissolve more sulfur dioxide, become more acidic, and then it's going to have more of an effect, right? And then, you probably hopefully remember from earth science, all the different effects acid rain can have in terms of corrosion of metals, and a whole bunch of other things. So that's kind of just interesting, direct connection here. Okay, so feel free to replay some of this video before you try the homework. There's just one document to read. Basically goes over everything I did. Some of these questions are even written out in the reading. I just kind of stole them directly from there. I figured it'd be useful. Yeah, so again, homework tonight, 10 questions, multiple choice. I think that is it. Yeah, and I will see you guys tomorrow or on Zoom. All right, see you later.